Hey everybody, Professor Long here, doing your A&P videos. This is going to be my respiratory lecture number 4 for my 2402 class, part 2 A&P. In the last lecture we were covering pulmonary ventilation, internal and external respiration, and we were talking about the movement of gases due to pressures, which is Dalton's law of partial pressure. What we're going to do next is we're going to go back over some of these concepts in a little bit more detail. We're going to talk about how do we accomplish particularly the pulmonary ventilation, which muscles are involved, and we're going to talk a little bit more about Boyle's law. Boyle was a scientist who figured or came up with this idea, at least was the first to write down the idea that pressure and volume in a closed system are inversely proportional. So we've talked about inverse relationships before. So let's talk a little bit about this. This is the equation. Pressure is inversely proportional to the volume. What that means is if volume increases, pressure decreases. Anytime I have a 1 over one of these two things, this is the truth. That also means if volume decreases, pressure increases in a system. Now, to visualize that, one of the things I like to do is think of a syringe. So if I take a syringe here, and let's say I got a 10 cc syringe, and I have the plunger pulled all the way back, and it's at 10 cc's, or cubic centimeters, or 10 milliliters, which are essentially the same thing. So I can measure the volume of fluid in this syringe. The pressure is low, the volume is high. Now, if I were to increase the pressure and press down on the plunger of the syringe, then what you would see is, and try to draw the same size syringe or roughly, let's say I push it down to only 4 cc's. Now look at the volume in the syringe. As pressure increases, volume decreases. So, this idea of pressure and volume in this situation under these circumstances being inversely proportional is kind of easy to visualize that way. Now, the reason I like to visualize it this way is because this area in here, where the fluid is in the syringe, and it doesn't have to be fluid, it could be the air in the syringe, is how your lungs work and how breathing works. The space inside here would be the space inside your alveoli. The opening here is we're going to express air through the oral or nasal cavities through the openings. And the plunger represents certain muscles. And the walls of the thoracic cavity, when they are pulled out and your diaphragm comes down, it increases the volume, which decreases the pressure. If the pressure inside this syringe is lower than the air pressure on the outside, it will pull air in. Air will always move from an area of high pressure to an area of lower pressure. When the pressure inside the syringe rises above the pressure out here, it forces the air out. Now, if the two pressures are equal, nothing moves. So we're going to see how our thoracic cavity works just like this syringe. Okay, and we're going to see which muscles are involved because this is important. So I'm going to erase this. Keep this idea of pressure and volume are inversely proportional. If volume goes up, or if pressure goes up, volume goes down. If pressure goes down, volume goes up. Or keep the idea of the syringe in your mind and think of this as the space inside the respiratory tract. And these are the walls of the thoracic cavity and your diaphragm. So let me erase this. Sorry, reach across here. Let me get my eraser and let's look at this. Okay, I'm going to draw 3 pictures going across here, but I'm going to start in the middle for a reason. Okay, so the first picture, I'm going to be a little bit more complete. So here's somebody's respiratory tract going down into the lungs. I made the lungs different sizes, and I should not have, but anyway, you get the picture. Okay, so there's the lungs. I can measure the pressure inside the lungs. If the pressure in here is called the intrapulmonic pressure. That's an A. Intrapulmonic, meaning the pressure inside the lungs. Here, let me rewrite that because it's not real clear. Okay, we write it out a little bit more neatly. It's called the intra, means within, pulmonic lungs pressure. Now, the pressure inside the lungs is going to be working with or against the pressure of the atmosphere. So this is going to be atmospheric pressure. And if we measured it with a person standing at sea level, so I'm going to draw another picture. It's just going to be an illustration to show you something. If I have someone high on a mountain and I have the earth coming down here and then the ocean, a person standing right here is at sea level. Now, what scientists kind of imagined, and the guys who figured this out did, one of them was a guy named Tor, is if I took a little certain size cube of air, how much pressure, how much weight and mass and pressure can that one cube of air provide? So imagine these little cubes of air stacked on top of somebody at sea level, all the way up to our stratosphere. Also imagine someone standing at a mountaintop who's not at sea level, has fewer boxes, less pressure stacked on them. This is going to be an interesting concept in a little bit. We're going to come back to this in a little while. But for the most part, if we took someone standing at sea level, the amount of pressure in the air pressing down on them can be measured. Now, the guy who did all of this, or one of the people that did, was a guy named Tor. And what he did was he took a U-shaped tube and he put some liquid in it. That liquid happened to be a metal that's liquid at room temperature, and he made it to where the volume of liquid on this open tube, the volume of liquid on this end, was equal to the volume of liquid on this side over here. And he said that is 0 millimeters, and he used mercury. Mercury is abbreviated Hg, but it's 0 millimeters of mercury. That's the chemical symbol for mercury. Mercury is a metal that is liquid at room temperature. It's the silver stuff that you see in the old school thermometers and in the sphygmomanometers when someone's checking your blood pressure. If it's the silver stuff, it's a metal. It's toxic stuff. It gets absorbed and gets stored in your liver, and your liver can't get rid of it or break it down, so it can poison your liver, so don't ever play with that stuff or touch it. By the way, I'll share a quick medical joke with you. What's the difference between an oral and a rectal thermometer? The taste. Sorry, I couldn't help that. Anyway, I told that to my physician. He tells that joke all the time. Anyway, so now, since this tube is open-ended, if I start to increase the pressure pressing down on this end, you could see that the mercury would start to rise. And we could measure how much the mercury would rise, and that measurement would be measured in so many millimeters of mercury. And what they realized is that at sea level, it happened to rise 760 millimeters of mercury, which sometimes is called 1 atmosphere. Okay, we're not going to talk about that. So we're going to use this 760 millimeters of mercury is the air pressure at sea level. So that's what we're going to use as our atmospheric pressure. Got it? Now, if someone goes up on a mountain, the amount of air pressing down on them is less, and we would see less movement of this mercury here. By the way, as liquids heat, you should learn this in physics and chemistry, the molecules start to move apart a little bit and expand. And so if you heat the mercury, it will also rise. That's why people say the mercury is rising when the temperature is getting hotter, or you're starting to feel pressure. You're starting to feel the heat if you're in a sticky situation. Anyway, so this is the concepts that we're going to use to understand this. Got it? We're going to be talking about 1 atmosphere or 760 millimeters of mercury, and we're going to be talking about the pressure inside the lungs. So now, I'm going to erase all this little illustration here. You have the concept in your head. And so if I take a person at sea level, the pressure of the air out here is 760 millimeters of mercury pressing into the respiratory tract. The intrapulmonic pressure, if we stop breathing and we're at apnea, is 760 millimeters of mercury if you're at sea level. So there's no air moving in or out at this point. Now, I'm going to try to use this red marker. Hopefully the red will show up pretty well. But I'm going to use this to represent the walls of the thoracic cavity. So out here we have our ribs and a whole bunch of muscle. and it would be sealed off. I may not draw it perfectly, but I'm just trying to illustrate a concept here. And we have our diaphragm, which the lungs sit on. Now, there's some serous membranes that surround the lungs. We're going to come back to those in a little bit, called the visceral and parietal pleura. One of the first things we learned early in part 1 A&P. The visceral pleura is up against the organ. It wraps back and forms the parietal pleura, which touches the walls of the cavity. And between them is called a pleural space. Well, there's some fluid in those membranes, and it kind of makes the membranes stick together and stick to the sides of the thoracic cavity. So wherever thoracic cavity goes, meaning the walls out here where your ribs are and your diaphragm go, the lungs will go with it. And this is literally like the plunger on a syringe. If I pull it down, the pressure will decrease and the volume of the lungs will increase, and vice versa. So what we're going to do down here is, on this side, we're going to do what's called quiet respiration, or what we call in our definitions last time, eupnea or eunia, true breathing or quiet respiration. In quiet respiration, you have to make note of this. Inhalation is active. We have to contract muscles and burn energy for inhalation to occur. For exhalation to occur, that's a passive process. Because of the elasticity and the stretchability of everything, when we let go, it's going to snap back. And as the volume is decreasing, the pressure is going to rise. So when we inhale, we're going to increase the volume of the lungs. Since these two pressures are equal, when the volume increases, the pressure will decrease and air will fall into the lungs or be pulled into the lungs because air will move from high to low pressure. When we exhale, as the lungs are falling back down, the pressure is going to rise greater than all of this and force the air out. And on each one of those, we are going to have a moment of apnea. And this is when we're at apnea. We've stopped breathing for a second and everything kind of equilibrates. Now, when we inhale, for inhalation, or we can also say inspiration, to inspire or inhale, take air in, what's going to happen is the picture will start to look like this. I'm not going to draw the head and all of that. I'm just going to draw the trachea and the bronchi. Now, obviously, this is an exaggeration because this is a drawing. I'm just trying to get a concept across, but if you look at it, I'm going to increase the volume of the lungs by flattening them out and pulling the walls out more, like this. And the reason that happens is because these muscles out here are pulling up and out this way on both sides. And the diaphragm has been pulled down. So this is your diaphragm. When your diaphragm, which is a skeletal muscle, contracts, it's like pulling the bottom of the plunger. When the external intercostals, these muscles are going to be the external intercostals. If you remember from the anatomy of the muscles, the external intercostals fibers run up and out between your ribs. When they contract, they pull your ribs out this way. As a matter of fact, if you can, do this. Sit quietly for a second, close your eyes, and breathe a few times. As you do that, you feel your ribs go in and out. That's the external intercostals for inspiration or inhalation during quiet respiration. These two groups of muscles really have to contract for you to inhale. The external intercostals and the diaphragm contract. What that does is the volume of the lungs the volume of the lungs increases. As the volume of the lungs increases, the pressure is going to decrease. And the pressure will actually drop down to, it's not a huge one during quiet respiration, but let's say on average it's 758 millimeters of mercury. Well, if the pressure out here is still 760, then the air, I'll do the air in blue, see if the light blue shows up. The air is going to fall into your lungs. That's inhalation. Now, also during quiet respiration, what's going to happen is those same muscles are going to be relaxed. Inhalation is active. Exhalation also called expiration, to expire or exhale, is passive. What that means is I don't need any muscles to contract. I simply relax the external intercostals and relax the diaphragm, and everything snaps back to where it was. In the process of going from here to here, the pressure is increasing as I'm squeezing down, forcing the air back out. And then I get to a moment of apnea. I stop breathing for a fraction of a second, and then I inhale, apnea, exhale, apnea. Inhale, apnea, exhale, apnea. Okay? So that's quiet respiration. Now, when we get to active respiration or hyperpnea, I'll write that over here. Over here, we're going to do the process of hyperpnea or active respiration. Okay, in active respiration or hyperpnea, what we're going to do is we're actually going to contract some muscles, some different muscles that are going to squeeze down on the chest and raise the pressure even greater above atmospheric pressure, forcing excess air out. Hyperpnea is that kind of breathing that we do when we're exercising. This is what you do when you're sitting quietly resting or taking a nap or sleeping. But when we get active, when we start working out on a treadmill, as I've stated before, what's happening, and a lot of systems, if you're in my class and hear me lecture normally, you've seen this equation so many times it's ridiculous. But I need glucose plus oxygen, run it through mitochondria to make all this energy. I get some water, I get some carbon dioxide. Carbon dioxide is building up in my tissues. And like we showed in the very first lecture, or I think the last lecture, when the blood hits the capillary bed, all that carbon dioxide wants to come rushing across that membrane and from the tissues into the blood, and all the oxygen comes rushing out of the blood into the tissues. So we're going to stick this carbon dioxide back into the bloodstream, and it's going to circulate around here. Carbon dioxide actually drives breathing more often and more frequently than does oxygen. Now, if oxygenation in a tissue decreases, we have mechanisms that will trigger the increase in respiration. But really, when we exercise, we build up excess carbon dioxide because the muscles, remember, have some myoglobin and their own glycogen reserves, and they burn a little extra sugar and oxygen. The oxygen's released from the myoglobin. The glycogen in the muscle gets turned into glucose, and they have their own little miniature reserve until our heart can start feeding it. And so we develop excess carbon dioxide. As the excess carbon dioxide is returning, it actually triggers a mechanism that does forced exhalation or hyperpnea. We're going to talk about how that works a little bit later. So what I want you to see is this. I'm going to try to draw this. Again, I'm going to erase this atmospheric pressure because it's a little bit in my way, but we understand that it's 760 millimeters now. Okay, so here's a trachea, bronchi. Here's the lungs. Again, I'm going to exaggerate this, but you can see how much smaller the lungs look here. And the reason that's going to happen is because some muscles here and the diaphragm are going to push down or pull in on the thoracic cage this way, and the diaphragm is going to be pushed up. Now, the muscles that contract up here are the internal intercostals. I don't know if you can read that or not. I'm looking at my computer screen as I'm talking to y'all, and I'm running out of room. I really do need to buy a bigger board, but I didn't know how this would work out. I think this week I'm going to go buy a bigger board and increase my view here. But this would be the internal intercostal muscles. Oops. I displaced or inverted my R and my C. The internal intercostals, remember, those are muscles between your ribs that go down and in, and when they contract, they pull your ribs in and squeeze down on your ribs. And then all of your abdominal muscles. I think everyone's seen a group of dudes standing around when a girl walks by, and they're all, well, you pull your abdominal muscles, and if you tighten up all your abs, particularly your rectus abdominis, but even some of the obliques, they're going to pull your guts in, and your guts, your viscera, are going to push up on the diaphragm, and it's going to force the air out. That raises the intrapulmonic pressure up to like 763 millimeters of mercury. And since I know it's only 760 here, then that's going to force all this extra carbon dioxide and air out of the lungs. So, under hyperpnea, or forced exhalation, exhalation is active. It's passive over here. I don't contract any muscles. I simply relax the muscles for inhalation, and now I actually squeeze out extra carbon dioxide. I get that extra carbon dioxide out, and then everything starts to snap back to its normal place. We inhale, and then we have some active inhalation all the way here. So we're actually getting much deeper, larger breaths. Normal breathing is inhale, active, exhale, passive. Inhale, active, exhale, passive. And then once you start exercising, you exhale extra, getting the extra carbon dioxide out, and then inhale extra, and then exhale the extra, inhale. And that's when you're huffing and puffing. So if you run up and down the stairs, or stood up and ran around your living room right now about 5 times, or ran around your house, you would be breathing like this. And you could feel your ribs and your abdominal muscles contracting, forcing the extra carbon dioxide out. So those are the mechanisms that are getting rid of that excess carbon dioxide. And this is why we have to have forced exhalation, to remove the excess CO2 from when we become very active under sympathetic activation. Also, sympathetic activation increases our breathing rate so that we get in extra oxygen, get rid of the extra carbon dioxide, while our little choo-choo train I drew before is going 90 miles an hour. Okay, so all that is the information that's on page 71 of your note set, and it's all in bold for those of you that have my note set, and I'll have a worksheet ready for you guys to do. But you really need to know which muscles are contracting for inhalation, and that during quiet respiration, it's passive. Those same muscles simply relax, and that causes air to move into and out of the lungs under quiet respiration. Under hyperpnea, or active respiration, when we're very active, then you also need to know that exhalation becomes active here, and which muscles are contracting, forcing the volume of the thoracic cage and the lungs to decrease. As volume decreases, pressure rises and forces the extra air out. And then as we snap back and continue to inhale, the volume is increasing and the pressure drops below atmospheric, and we pull extra air in. Okay? So know those things, understand them, know that they're under sympathetic control for the active respiration. We'll a little bit later on, we'll go into which parts of the brain actually control these muscles. The ventral and dorsal respiratory groups, the apneustic, and the pneumotaxic centers. All right? So I hope you learned something in this video. Hope you had as much fun as I did. There will be a worksheet coming for my students. If you're not in my class, well, maybe this made it a little bit more easy to understand. All right? All right. Have a good day, and see you in the next video.